The last cost estimation technique in this chapter is regression analysis. We know that the formula for a straight line is y equals a plus bx, where y is the outcome variable and x is the predictor variable. For Charlene's computer care, y is the total overhead cost and x is the number of repair hours. And we believe that the relationship between those two variables can be described by a straight line. We've already used the HighLow method to estimate that equation, but the HighLow method only uses two data points to define that line, the highest activity level and the lowest activity level. It does not use any of the points in between. Because of that, we really do not know whether the model is actually a useful predictor at all levels of activity. By contrast, regression analysis considers all of the data points when it estimates this line. And since it uses all of the data points, it can tell us how good the model is, how close all of the data points are to that line. Here is a regression analysis that was made using Excel for the data in the Charlene's computer care problem. Let's take a look at some of the things that it shows us. Multiple R is the correlation coefficient. In other words, it tells us whether a straight line is a good way to describe the relationship between the predictor variable and the outcome variable. If R is very close to 1, that means there is a strong positive correlation between the predictor and the outcome variables. In other words, as the predictor variable goes up, the outcome variable also goes up. If R is very close to -1, there's still a strong relationship, but it is a negative relationship. In other words, we would expect that as the predictor variable goes up, the outcome variable goes down. That didn't happen in this case. Either way, the closer R is to +1 or -1, the better the data fits a straight line. On the other hand, if R is very close to 0, that means that there is no strong correlation between the predictor variable and the outcome variable. In other words, knowing something about the predictor variable doesn't tell us anything about the outcome variable. The two are not related. In this particular case, the correlation between repair hours and overhead costs is very high. They are correlated with each other, and that suggests that a straight line is a good way to describe their relationship. Now let's take a look at R squared. That's called the coefficient of determination. And what it tells us is the proportion of the variability in Y that is explained by knowing something about X. As R squared gets closer and closer to 1, that means that our model has more explanatory power. If R squared was 1, that means knowing X would tell us everything that we need to know about Y. But As r squared gets closer and closer to 0, that means the model has less and less explanatory power. If r squared was 0, that would mean that knowing the predictor variable would tell us nothing about the outcome variable. That didn't happen here. In this case, knowing the repair hours explains about 82% of the changes in overhead costs. Standard error tells us how tightly the actual data points fit to the regression line. If you look at the graph, the data points are very, very close, and therefore the standard error is very small. If the data points were very far away from the line, then standard error would be much bigger. The model is better when the standard error is smaller. Observations tells us how many data points were used in the analysis. Now let's take a look at the lower part of the regression output. The y-intercept is the place where our straight line crosses the y-axis. In our model, that represents fixed cost, the amount of our overhead cost that would be there regardless of our level of activity. And our regression tells us that our fixed overhead costs are estimated to be $6,472. Repair hours represent the slope of the line. In our example, that's variable overhead costs, and our regression estimates that to be $12.52 per repair hour. So our total regression equation is our overhead costs will be equal to the fixed component, $6,472, plus the variable component, $12.52 per repair hour times X, the number of repair hours. So, for example, if we wanted to estimate how much our overhead costs would be if we expected to use 480 repair hours, we would plug 480 in the equation for X, and that would give us our estimate of our expected total overhead costs. Now, how good is this prediction? There are a couple of ways to tell. We know that the formula for a straight line is y equals a plus bx, and in that formula, b represents the slope of the line. If b is equal to 0, if the line is flat, that means all of our costs are fixed. There is no variable component to our costs. The t-stat tells us whether the slope of the line is significant, that is, significantly different from 0. And it's computed by taking the coefficient b and dividing by the standard error of b. The general rule is that if the t-stat is greater than 2, then b, the slope of the line, is significant. In this case, both of the t-stats are significantly higher than 2. That means the slope makes a difference. Not all overhead costs are fixed. The p-value represents the chance that the relationship between x and y that we have observed occurred only by coincidence. We would like that chance to be very, very small. In this case, there is an extremely small chance that repair hours and overhead costs are actually unrelated. That's good news for our model. The lower 95% and upper 95% are called the confidence interval. That is, how big of an interval around the predicted coefficient do we have to have in order to be 95% confident that the true value, which we can't see, is within that interval. We compute the interval by comparing the coefficient to the standard error. The lower bound is computed as the coefficient minus the standard error. That's the lowest expected value. And the upper bound is the coefficient plus the standard error. The better our model is, the smaller the interval has to be in order for us to be 95% sure that the unseen true value is within that interval. So in this case, having a tighter confidence interval is better news. In this case, it's showing us the range for which we can be 95% confident that the true value is within that range. This confidence interval is very small, and because of that, we feel pretty confident about our coefficients. Now, here's the problem. Our model tells us that repair hours only predict about 82% of the changes in overhead cost. So Charlene was wondering whether there might be another predictor variable at work. So she decided to do multiple regression. That simply means a regression with more than one predictor variable. In this case, she decided to use repair hours, and she also wanted to include parts cost on the theory that the more parts cost she incurred for various jobs, the more overhead she would incur for ordering parts, for moving parts around her shop, and so forth. This is what her predictor equation would look like, where y equals the total overhead cost, A is the portion of her total cost that is fixed, B1 is the variable cost per repair hour, and we're going to multiply that by the number of repair hours. B2 is the variable cost per dollar of parts, and X2 is the total parts cost. Regression analysis is a wonderful technique for predicting costs. However, there are still some problems. One issue is trying to use a straight line to fit non-linear data. We can see from the graph that the straight line doesn't fit the actual cost function even within the relevant range. One way to solve this problem would be to define a more narrow relevant range where the straight line is a better predictor. If that doesn't work because you need the wider range, you might want to use different regressions for different areas within the relevant range. Or if you need to have a non-linear function to describe your data, don't choose a linear model. There are regression packages that would allow you to use more complicated formulas. Another issue in regression analysis is outliers. An outlier is a data point that does not fit well with all of the other data points. So most of the data points are telling one story, but this one outlier is telling a different story. The graph shows an example. Here's our outlier. It seems significantly different from all of the other points. If we include that outlier in our regression, it's going to tend to pull the regression line down toward it. However, if that one data point shouldn't really be there, it was there due to a typo in the database, let's say, then our computed regression line is going to be significantly different from the unseen true regression line. So how do we handle this? The first thing we do is prepare a scatter graph, as we did with this data, and look at it very carefully to see if there is a data point that does not seem to fit with all of the others. In that case, we should investigate that data point and find out whether it was a typo in the database or there was some other factor going on. And if we believe that that is not a good data point, we should eliminate it from our analysis, because otherwise it will distort our understanding of the correct regression line for all of the other data points. Another problem in regression analysis is using inappropriate data. Regression will tell you a relationship, but it may not be a relationship that makes sense. For example, supposing we use direct labor hours to try to predict materials costs. There is no reason to think that there is a relationship there, so any regression equation that we create may have numerical answers, but they won't be useful to us. Therefore, before we do any regressions, we want to test our variables for reasonableness. Look at them and make sure that the model that we are creating has face validity, makes sense on the face of it. There are some other potential data problems. We may find that we're missing data. We may not check for outliers. We may have ridiculous relationships between predictor variables and outcome variables. Our costs might be affected by inflation, or we may be trying to match costs in one period with activity levels in a different period. Altogether, what this tells us is that decisions are only as good as the information on which they are based and the skills that we use to make them. If we have bad information, then it doesn't matter how skillful we are. We're not going to come to a good conclusion. On the other hand, if we have good information and we use it badly, we still won't come to a good conclusion. Regression analysis is a powerful analytical technique, and if you become familiar with how to do regression analysis through Excel, it can be very helpful to you. Number one, we already have the data, so doing the regression is not that difficult. Number two, we can process huge amounts of data quickly and easily. And number three, regression analysis will always tell us how good, how reliable, how descriptive our model is. However, it's not a perfect method. It does have disadvantages. One disadvantage that we already discussed is the possibility that our data is non-linear. In that case, the straight line that regression analysis gives us will not be useful to predict our outcome variable at all levels of our predictor variable. So, here are the results from the 3 methods that we used to try to predict overhead costs for Charlene's computer care. This was the result that we got for account analysis. Here's our result for the HighLow method, and we notice that the HighLow method estimated a larger amount of fixed costs and a much smaller amount of variable cost per repair hour. Here's our result from regression analysis, and we notice that the fixed cost was somewhere in between the other two, and the variable cost was a little bit higher. So which measure is correct? To answer that question, we would need to know what the true values are. And if we knew the true values, we wouldn't need to use a cost estimation method. So that question is unanswerable. The best that we can do is to choose a method that gives us a reasonable answer and does not require more work to get the answer than the benefits that the answer will give us. In this particular case, I would recommend regression analysis because it not only estimates our fixed and variable costs, but also gives us measures of how reliable those answers are.